Okay, let's do this question again using the cylindrical shell method. Now, as I mentioned to you before, in the cylindrical shell method, we are taking one slice that is parallel to the axis of rotation. So let's take one slice. Okay, so form a cylinder, and we are adding up all of cylinders to find the area of the torus. Now, although we can use both methods, slicing and cylindrical shell, to do this problem, you will see why the HSC question actually asks us to use slicing rather than cylindrical shell, because algebraically using cylindrical shell to solve this problem is a lot more difficult compared to slicing. Okay, now in the cylindrical shell method, so let's firstly find the volume of these thin cylinders, and the technique that we use here is, imagine that we have a thin slice and we're going to roll this out into a very thin rectangular prism. Okay, now to find the length of this rectangular prism, the length is equivalent to the circumference of this cylindrical shell. So to find the circumference, first of all, we need to find this distance here. And we can see that at any particular point, this distance is x unit from the origin. So that's x. So therefore, the length of this rectangular prism must be 2 pi x. Now the height, now at this point to this point, so from here to this point is y. Since you go all the way down here, so this must be 2y. So the height of this rectangular prism must be 2y. And the width of this is changing in terms of delta x, because we're adding in from here all the way up to here, and we are changing in terms of in the x direction. So that's the width. Okay, now to find the volume of this slice, delta V must be the length times the height times the width. Now the volume is equivalent to taking the limit of delta x approach 0, summing this up from x equals 2. Now coming back to our diagram here, we're summing up the distance from here, this point, to this point. Now the center of the circle is A0, okay, and then the radius is B. So from here to here, this point here must be A minus B, and this point here must be A plus B. So we are summing this up from x equals to A minus B to A plus B. Now this is equivalent to the integral from A minus B to A plus B. Now let's take out the constant 4 pi at the same time, since we're integrating with respect to x, changing the y in terms of x. Now if you solve this, we can see that it's y squared equals to b squared minus x minus a squared. So y equals to plus and minus square root of b squared minus x minus a all squared. So we have x multiplied by square root of okay, to give the volume. Okay, here we take the positive square roots instead of the negative, because we can see that this is from the circle here, the two function is symmetrical about the x-axis, so it doesn't matter which one you take, but of course taking the positive is more convenient comparing to taking the negative. Okay, let's continue this integral. Okay, now to solve this integral, we need to use a very small algebraic trick. So what we're going to do here, we're going to say a plus x minus a. Now notice the a's, they cancel out, so it doesn't really change anything. Okay, and then we're going to split this up. Okay, as you can see here, this is why we should use the slicing method rather than the cylindrical shell. As you can see, the algebra here is very difficult. But regardless, we can still integrate this. Let's take a out. Then the remaining part, this part, is equivalent of finding the area of the semicircle at center at A0 with radius b. So the area of this semicircle would be pi b squared on 2. Now to integrate this, we can use the reverse chain rule, which gives us b squared minus x minus a all squared to the power of 3 on 2 over 3, and evaluate this from a minus b to a plus b. Now this first part here, simplifying it, we get 2 pi squared ab squared. Now this part, you can see that when you put in a minus b in here, then you just get b squared, and b squared minus b squared gives you 0. So this entire thing will give you 0, minus, when you put in a minus b in here, you get minus b squared. But when you do b squared minus b squared, you get 0 as well. So you have 0 minus 0. So this entire part here is equivalent to 0. So therefore, the volume is equal to 2 pi squared ab squared, which is exactly the same as the answer from the slicing method. There's actually a very simple way to check whether your final answer for this torus is correct. It's called the Pappases Centroid theorem, which states that the volume of the solid of revolution is equal to the product of the cross-sectional area and the distance traveled by the cross-section centroid. Okay, now that we know what this theorem says, let's use this theorem to check our answer for this torus. First of all, we need to find the area of the cross-section. You can see that this is area of the circle with radius b. So the area must be pi b squared. Now multiply by the centroid, the distance, multiply by the distance traveled by the cross-sectional centroid. So in this case, our centroid is the center of the circle, A0. So this distance, which is distance A, traveled around the y-axis. So you can see that it must be a circumference. To find the circumference is 2 pi a. So simplifying this, we get 2 pi squared ab squared. And you can see that this answer is consistent with the two answers that we've got in the previous two methods. Now, one thing to note is Pappases' centroid theorem is only useful to find the volume of toruses, because The centroid is very easy to find, which is the center of the circle. Although this theorem applies for other shapes, but sometimes if you have irregular cross-section, the centroid is very difficult to find, so it's not very applicable to those questions.